Hey guys, what's up and welcome back to the Rocket Hub. My name is Philip and today we are continuing our series about the Raptor engine and take a closer look at some serious design challenges and their solutions. This is the ultimate Raptor engine render.
3, 2, 1.
What you are currently watching is part 2 out of 3 of the series about the Raptor engine. Large sections of this video build upon the stuff from part 1, so you should watch part 1 before going on with this video. And because this is part 2, we are going to start with chapter 4 and not chapter 1 as usual. Again, here are timestamps for the entire series, so you can always jump around the videos to find what you're looking for. I promise this is the last disclaimer, but there is a third part of the series as well, which builds up on the video you're currently watching. With all disclaimers being disclaimed, let's go on with part 2 of the ultimate rundown on the Raptor engine. Since the last video, we know everything about combustion cycles and rocket fuels and why SpaceX decided the way they did when choosing their fuel and combustion cycle. We are now going to leave the theoretical area of general propulsion theories and enter the actual design of the Raptor. The Raptor engine has quite a few interesting design solutions incorporated in it. Among them are the insane capabilities of engine throttling. But to understand the incredible work the engineers at SpaceX accomplished, we first have to understand what we are even talking about. Liquid rocket engines aren't just running on full power. Other than solid rocket motors, they can produce more or less thrust whenever they are needed to. And there are quite a few scenarios in that a liquid rocket engine has to throttle itself up or down by quite a bit. Maybe the most remarkable of those scenarios is the so-called max Q. Max Q is a specific point during the ascent of a rocket around 1.5 minutes after liftoff, but that varies from vehicle to vehicle. Max Q refers to the moment in that the vehicle experiences the highest aerodynamic loads during ascent. When the vehicle accelerates, it moves faster relative to the air around it. But at the same time, the atmosphere gets thinner, so there's less air around the accelerating vehicle. The two curves of the vehicle's velocity and the atmospheric density are antidromic graphs. The vehicle starts at zero and gets faster over the time, but the density of the air around it decreases steadily. So one curve is climbing and the other one is falling. Aerodynamic loads are basically the combination of both curves. By combining both curves, you get a graph that basically looks like this. It starts at zero with maximum air density but no speed, rises during the vehicle acceleration, reaches a peak, and falls off again with decreasing atmospheric density. At the end, it reaches zero again because there's simply no air anymore. And the peak in the middle of the graph is what engineers know as max Q, the moment of highest aerodynamic loads on the vehicle during flight. But max Q requires the vehicle to be a lot more resistant against aerodynamic forces, only to safely survive just about 20 seconds of the entire flight. Optimizing a rocket to withstand max Q causes conflict with the ideal designs for other phases of the mission, like the further ascent or the in-space behavior of the vehicle. That's a huge engineering problem here. But the solution engineers came up with is not redesigning their vehicle for higher aerodynamic forces, but instead reduce those forces. Of course, you can't just change the density of the air around you. But the other factor for the aerodynamic loads equation is vehicle speed and indirectly acceleration, and that's changeable. What rockets do is throttling the engines down a bit so they generate a bit less thrust. Now the rocket accelerates slower than it did before, and its speed increases not as much as on full engine power. And if you throttle the engines down just before max Q and back after it, the curve of aerodynamic forces gets flattened, the peak loads are way lower. By using this simple trick, engineers increase the safety of the vehicle and decrease the mass of the vehicle at the same time. Almost every rocket developed until now did throttle its engines for max Q. The Falcon 9 does it, the Saturn V did it, the Space Shuttle did it, and Starship will throttle its Raptor engines as well to decrease max Q loads. Most of the time, the throttle range during max Q lies between 80 and 95% of maximum thrust. That's why the most engines can throttle down further than about 70% or so, because that's almost always enough. But other than traditional rockets, the Raptors don't just throttle down at max Q. SpaceX wants to reuse the vehicle and it needs to land vertically. And to slow the vehicle down, they need the main engines of the vehicle to run for the necessary reduction of speed. But landing a rocket requires insane control over the amount of thrust the engine produces during the landing attempt to perfectly cancel out the velocity of the incoming vehicle. The velocity has to hit zero exactly in the moment of touchdown, or the landing attempt will fail. Too much velocity results in impact, and too much thrust could cause the vehicle to climb into the sky again and then fall down to the floor when the fuel is running out. To avoid those scenarios, the engines have the ability to be throttled in real time and need a much more wider throttle range. A Falcon 9, for example, lands with just one of its 9 engines running, and that engine isn't even running on full power. And Starship has just 3 engines instead of the 9 Merlins on a Falcon 9. One Raptor produces more thrust than 3 Merlins at full power. To land perfectly, SpaceX would need to relight just one of those engines and throttle it down a bit for the landing burn. But running the landing burn on just a single Raptor has proven to be not that reliable in the past, as SM-10 died to prove that. So SpaceX decided to land on 2 Raptors instead of 1 for higher reliability and redundancy. But to avoid generating too much thrust with those 2 engines, the engines have to be throttled down to about 40% of maximum thrust, and SpaceX even plans to reduce that to about 30% or even less. The Raptor engine has the largest throttle range of all rocket engines ever developed to accomplish the task of landing a Starship safely. And engine throttling isn't even the only thing SpaceX needs for landing control. The 3 Raptor engines on the base of Starship have to gimbal quite a lot for better control and stability during a powered landing attempt, and that in a relatively quick succession. Gimbaling may not be exclusive to a Raptor engine at all, but the Raptor is one of the only engines we have seen the actual gimbal mechanism of. Engine gimbaling is used to create thrust vector control over the vehicle. By gimbaling its engine, Starship can move in every horizontal direction without the actual Starship tilting, and it is essential for the belly flop and the landing flip maneuver. And additionally, the gimbaling of the engines ensures the Raptors do not crash into another during the engine ignitions and shutdowns. The system SpaceX uses on the 3 center engines of Starship is basically just made up of 3 beams and a few motors to retract or extend those beams. The beams are arranged in an equilateral triangular setup, with the distance between all the 3 beams being identical. One side is attached to the engine and the opposite end to the thrust dome of Starship. By retracting those beams, the whole engine, not just the nozzle, gets tilted. Now the exhaust is pointing away from the center of the rocket and can be used to either create horizontal movement or lever arm to flip the vehicle around. And due to the triangular setup, the engine can theoretically be pointed in every direction to a certain angle. The Raptor has the ability to gimbal a whopping 360 degrees. But in operation, that is just possible on vehicles with just one Raptor, and since that won't happen ever again, the engines are restricted to gimbaling towards the outside of the vehicle and therefore away from the other engines. If they were to gimbal towards the center of the vehicle, they could damage themselves, so they won't do that. All in all, the gimbaling system is probably as simple as it can get. You could even try to rebuild such a system with Lego bricks if you wanted to. Great solutions to engineering challenges aren't always as complex as a full flow stage combustion cycle. No, the secret is to simplify the systems as much as possible. And with the gimbaling system, SpaceX has done exactly that. Both engine throttling and gimbaling aren't exclusive to a Raptor at all. In fact, nearly every liquid rocket engine does throttling and gimbaling at some point. But the engineers of the Raptor have taken these two mechanisms to a whole new technical level, allowing them to simplify the systems and squeeze even more performance out of the engine. And in terms of gimbaling, no engine is easier to understand than the Raptor is. A liquid-fueled rocket engine burns fuel in its combustion chamber under enormous pressure and temperature. The combustion chamber is in case of the Raptor and almost every other engine made of metal alloys designed to withstand the immense forces of combusting liquid fuels. But the combustion temperature is too high for the engine to withstand without any further external cooling systems. And of course, the Raptor engine has the same problems. The pressure inside its main combustion chamber is over 330 times as high as sea level air pressure, and the temperature inside a chamber often exceeds 3000 degrees Celsius. And despite the engineers at Hawthorne having done some incredible work in developing heat-resistant superalloys, those temperatures are simply too much for some parts of the engine to withstand. To solve this problem, the Raptor engine was designed as an expander cycle engine. That has nothing to do with the actual combustion cycle as it may sound, but it involves the flow of the rocket fuel through the engine as well. An expander cycle engine basically means that the rocket fuel is not only used to create thrust, but instead used to cool essential parts of the engines too. In most cases, the fuel is pumped through pipes running across the surface of these special parts of the engine, and in some rarer cases, even right through them. Those parts of the engine mainly involve the perimeter wall of the combustion chamber, the nozzle, sometimes the preburners, and especially the throat. The throat is the connecting piece of a combustion chamber and the nozzle. It is essential for keeping the pressure inside the combustion chamber high and at the same time directing exhaust in the right direction. But the throat has such a small diameter that the friction the exhaust causes when passing right through it heats it up to immense temperatures, even beyond anything created by the actual combustion itself. To keep parts like the throat at operating temperatures, engineers pump nearly all of the liquid fuel through pipes on the surface or even inside of those super hot parts. And luckily, we know how exactly the fuel circulates in the Raptor to keep it cold. Let's go back a bit to the full flow stage combustion cycle stuff. Remember this simplified version of the cycle? Well, that's not what the setup of the preburners is actually like. Due to all the cooling systems and heat exchangers, the oxygen pump and preburner aren't on the right, but rather placed right on top of the main combustion chamber. Now our version of this cycle looks more like the actual engine. But wait, where are all the liquid fuel-based cooling systems? Well, here they are. I left them out, and if you see them, you probably know why I left them out. As you can see, those cooling systems are way too complex to depict on our simplified combustion cycle, but luckily there is an amazing render of the Raptor engine cut open by Corey aka Cbus Productions that shows all of the fuel pipes and therefore even the cooling systems. In the Raptor, every single bit of liquid methane goes through the cooling systems for maximal heat exchange. The more fuel you pump through your engine, the more heat it can absorb. Makes sense, right? The methane's journey through the Raptor engine begins in the methane turbopump, where it gets squeezed into the Raptor's pipes with enormous pressure. Once pressurized, the methane automatically flows through the entire engine to the preburners, which create the massive underpressure. Since fluids always flow from high pressure to low pressure, the methane is sucked through all those pipes without the usage of any additional energy or pumps of some kind. After passing the turbopumps, the methane is led into a thick pipe that goes around the throat of the engine. Since the throat is by far the hottest part of the engine, it needs the most cooling. Therefore, the cryogenic methane gets pumped to the throat before reaching any other part of the engine, because every cooling system warms the methane to a certain degree. When the throat is reached, the methane is still as cold as it can get, but gets slightly warmed up by cooling the throat's outer perimeter. From a thick pipe around the throat, the methane reaches stage 2 of the cooling cycle, the wall of the combustion chamber. It is led directly into the chamber's wall. Yes, that is right, into the wall. Other than you might think, the combustion chamber wall isn't massive, but instead made of two metal alloy sheets with some empty space between them. And this small space is where the fuel flows through. By having this cooling layer of liquid in between the two edges of the wall, the combustion chamber wall doesn't get nearly as hot as it would without that layer. The fuel circulates around the entire combustion chamber before being led back to the throat. Actually, the throat is being cooled twice, since there is the big pipe going around it, and the wall of the throat has the methane channel in it as well. Through that channel, the methane flows down to the third cooling system and through the Raptor's nozzle. And the nozzle has even 3 layers of metal alloy and in its wall, and between them 2 channels for methane. In the inner channel, the liquid methane flows down to the very bottom of the engine and gets warmed by all the heat it absorbs. To get all this warm methane back up to the preburners, the outer channel exists. Have you ever asked yourself why the nozzle of the Raptor doesn't glow like the one on the Merlin vacuum engine? That is because of the Raptor's expander cycle cooling system. If that system didn't exist, the Raptor would most likely begin to glow like the MVAC with its radiator nozzle and then fall apart due to overheating. All of the 3 cooling system stages are one significant part of the engine, and without them it wouldn't work. Getting the cooling of the engine, especially the throat, done is a quite difficult challenge. Not every engine tackles as easy as the Raptor does. Although we haven't got any information on its design, the cooling systems of the Raptor vacuum variant may differ from the ones on sea level engine we were talking about the whole time. Since the actual engine, the preburners, combustion chamber, and all of that stuff is almost identical on both engine variants, we can expect the cooling of both throat and combustion chamber to be the same double-walled design as on the sea level engine. But on a nozzle, the regenerative cooling of the base variant may get replaced by something else. The Merlin engine, the engine used to power the Falcon rockets, is also regeneratively cooled. But on the vacuum engine, SpaceX simply ditched the regenerative cooling and went for radiative cooling, meaning the heat just gets radiated out into space. That's why the nozzle of the Merlin vacuum always glows orange. Considering that, the vacuum Raptor may be cooled radiative as well. On the other hand, there are structures visible on a vacuum Raptor that look like pipes. There's one ring about in the middle of the nozzle and a second one at the very bottom of the engine. Between them, there are many smaller pipes connecting the 2 rings. And there's one big pipe coming from somewhere around the combustion chamber that leads into the upper ring. Such a piping system clearly points towards being regenerative cooling used as well on the airvac, although that isn't finally confirmed yet. Another engineering challenge the creators of the Raptor had to tackle is the ignition process. Rocket engines don't behave like the electric motors of a Tesla. You can't just press a button and your engine starts to generate thrust. That's not how it works. The ignition process of a rocket engine is pretty complicated and is a serious challenge to tackle, and in the case of the Raptor, the ignition process failing has already caused the loss of the SN9 test vehicle. If an engine doesn't light in the right moment, the mission is almost certainly a complete loss. Although engine ignition might seem trivial, it is way more complicated than you might think. Remember what I mentioned in part 1 when we talked about these beautiful combustion cycles in regard of pressure? If you don't, here's a small reminder. Gases always flow from areas with high pressure to areas with low pressure. Therefore, the engineers of rocket engines raise the thrust in the engine's combustion chamber to immense values of multiple hundred times the ambient pressure of the air. By doing this, the exhaust gets sucked out of the engine and contributes a lot of energy to move the rocket. But to achieve such pressures, the turbopumps are needed to push all the fuel into the engine. And those turbopumps are powered by a turbine wheel which is positioned in the exhaust trail of the preburner. It's basically a small rocket engine inside the actual engine. But there is a major problem involving the preburners. To start the preburners and therefore the turbopumps, the fuel must already be pressurized. That means turbopumps have to be running for the preburners to work, but the turbopumps need the exhaust of the preburners to spin, but the preburners need the turbopumps to run, which require working preburners. Damn, we are in an infinite loop of something requiring something else to work, and without any external help, the rocket engine would be unable to start. So, how do engineers solve this problem? Well, there are two different approaches to solve this infinite loop. One of them is what SpaceX is doing with the Merlin engine used on the Falcon 9 and Heavy. To get the engine to operating pressure, they don't start the preburners with the actual fuel, in this case RP1 and oxygen, but instead with the so-called ignition fluid. For a fraction of a second, the preburners burn something else to spin up the turbopumps, and if the pumps are once running, the fuel is pressurized enough for the preburners to work, and the combustion of ignition fluid is cancelled. In case of the Merlin, this ignition fluid is the so-called triethyl aluminum triethyl borane, and because even chemists hate their unpronounceable molecule names sometimes, they of course have an abbreviation for it: TTAB. In a special reaction, the triethyl aluminum reacts with the borane and spontaneously combusts when thrown together. This combustion of TTAB is even visible from the outside, especially in slow motion. Right in the very second of engine ignition, a bright green flash can be seen coming out of the engines. That green flash is the exhaust of the combustion of TTAB, which burns with a bright green flame. But the Raptor engine doesn't create these green flames on ignition. And no, the green flames we have seen on multiple test flights weren't TTAB, that was just the engine combusting itself. On Starship, additional ignition fluids aren't the best way to go, since ignition fluids are in conflict with Starship's ambitious purpose. Something like TTAB is an additional consumable that has to be refilled constantly, since the tanks only support a small number of ignitions. For a fully usable vehicle that is set to go to Mars and back, the tanks for ignition fluids would have to be fairly large, and that would add a lot of dead weight to the vehicle. And additionally, ignition fluids are often contradictive for engine reusability, something the Raptor should bring to the next level. So, if ignition fluids are not suitable for a Raptor engine, how does it ignite? At the beginning, I mentioned there would be two ways to start the turbopumps. One way is igniting the preburners with a different fluid like TTAB, and the other one is what the Raptor does. The Raptor engine doesn't ignite the preburners before the turbopumps, but instead it works pretty much the other way around. It starts the turbopumps before the preburners ignite, so that the preburners don't burn anything else than methane and oxygen. This mechanism is also sometimes referred as the turbopump spin start. Instead of some kind of ignition fluid, the Raptor blows compressed air provided by a composite overwrapped pressure vessel, short COPV, straight into the turbine that powers the turbopumps. Once the turbopumps are running and sucking fuel into the engine, the preburners ignite and the combustion starts. The whole process of spin starting the turbopumps is even visible from the outside. When Raptor initiates startup, the first thing that comes out of the nozzle is a cloud of white steam. That steam is actually the gas used for spinning up the turbopumps. You can even hear the compressed gas flowing through the engine as a loud fizzing noise during the beginning of the ignition process. The main advantage of taking an approach similar to the Raptor instead of ignition fluids like T-Tap is easier refueling. Compressed air isn't that hard to get on Earth and even on Mars, increasing the Raptor's capabilities in terms of reusability dramatically. In the rocket engine, the ignition process usually involves not just one ignition, but the ignition itself happens in two stages. What we have been talking about so far was the first step of ignition, the startup of the turbopumps and preburners. The second stage happens in the main combustion chamber, since igniting the preburners doesn't start the combustion there. Rocket engines need a second ignition process for the actual combustion chamber. Many engines use the same ignition fluid that is used on the preburners to start the combustion in the main combustion chamber too. That may smaller the need of additional systems, but requires even a higher amount of that ignition fluid. Once ignited, the combustion chamber burns self-sustaining and needs no further igniters to continue combustion. Another commonly used method of igniting main combustion chambers is using single-shot or sometimes multiple-shot pyrotechnical devices to ignite the chamber. But such igniters are usually not able to be reused, since most of them have just enough fuel to power less than 3 times. Sadly, we don't know much about the actual design of igniters of many engines, since that information is classified. But what we know is that the Raptor is again taking an approach that nearly no other engine of today follows. Instead of using some kind of pyrotechnical devices or ignition fluids, the Raptor uses dual redundant spark plug torch igniters. These igniters create the spark used for ignition not by some kind of combustion, but rather by receiving an electrical impulse. With a bit of electricity, they can create a spark that reaches the combustion chamber, which is already filled with the explosive methane-oxygen mixture, just waiting for the spark to ignite it. SpaceX hopes to achieve higher reliability and reusability by making this drastic change to their igniters. After all, they want to have the Raptor lasting for 1,000 flights, so that change was probably needed. By finishing up our section on the engine control, cooling and ignition systems, we have already reached the end of the second part of the Ultimate Raptor Engine Rundown series. But there is still part 3 left, in which we'll take a closer look at some of the other stuff that makes the Raptor special and then compare its performance to other remarkable engines, and at the end, we are going to draw a conclusion of everything we've talked about. Part 3 we will link in the outro screen, and it's already linked in the description when it's released. All of my videos, and especially the one you're currently watching, cost me a lot of time to script, record, and cut. It's a lot of work for me to give you the content you deserve, so I would really appreciate it if you hit the like button, share the video with your friends, and subscribe to the Rocket Hub. Thank you for that. We see ourselves again in part 3 of the series, and until then, I'm out. Cheers!